Okay, so we are going to talk about primes today. So let's start with the definition. So I'm sure all of you know. So let's say n is a positive integer. Then n is a prime. It's defined to be a prime if n has exactly two factors, 1 and n itself. Okay, so if these are the only two numbers that divide n, then n is a prime. Otherwise, n is composite. So conventionally, 1 is considered neither to be a prime nor a composite. We'll leave out the details right now, but let me define the set of all primes as P. So P is a set of all primes, and let's write down some primes. So as I said, 1 is conventionally neither a prime nor a composite. 2 is definitely a prime, and in fact 2 is the only even prime because any other even positive integer will have 2 as a factor. So 2 is the only even prime, and then 3 is a prime, 5, 7, 11, 13, and so on. Okay, there are many more. I'm not listing them, but you get an idea with the definition that these are the primes. So our focus is going to be in fact on this part. Okay, when I said dot dot dot, I implicitly meant that yes, there are many other primes. I'm not listing them right now. Maybe it will take time. I just don't want to spend that time. That's okay. But maybe there are more. I don't want to list them right now. That's the question that we are going to look at. How many primes exist? In fact, we'll prove this claim that there are infinitely many primes. Okay, so let's go back to this part, dot dot dot. So as I said, I mean, I can list down more primes, but it will take some time. But the real question is, if I give you enough time, then will you be able to list all of them? Okay, so this claim in fact tells you that no, it's not possible. There are infinitely many primes. That means no matter how much time I give you, you will never be able to list them all. Okay, this process of listing the primes will never end. So that's what it means, that you will not be able to do this in a finite amount of time, and there are indeed infinitely many primes. So we will prove this now. We'll prove this claim, and this is a proof by contradiction. So let me first present the proof, and then we will talk a little bit about this general strategy of doing proofs by contradiction. So the first step that we do in any proof by contradiction is we assume that the claim is false actually. Okay, what it means in this case is that we will assume that the claim is false. That means it's not true that there are infinitely many primes. In other words, there are finitely many primes. That is what we will assume. Finitely many primes. Okay, so how many? Maybe k many. Okay, k can be any number. It can be 1000, 10 to the power 6, whatever. I mean, 10 to the power, I don't know, 100, some huge number, but it's a fixed number. Okay, so how many? Maybe k many. So k is a fixed positive integer, and exactly those many primes exist. That is what we assume. Okay, so I can list down this set, right, as p1, p2. Again, I'll have to use dots here, but then that enlisting will end here at pk. There are exactly k many primes, so I can label them each with some index p1, p2, p3, and so on. Okay, so now let's define n to be the product of these primes. So it's a product of p1, p2 up to pk, that product plus 1. Okay, so given that I'm able to list this set in a finite amount of time, I can also take the product. It's a well-defined product, and I'm just adding 1 to that, and that I'm calling as n. That's a definition I'm giving. So let's observe a few things here. N is greater than 1, right? Because it is 1 added to something, and this something, this product, is definitely more than 1, because 1 is neither a prime nor a composite, and it's a product of positive numbers, so N is definitely more than 1. This is first observation. In fact, we also observe that N is more than every Pj in this set. Okay, I mean, that is also a very simple thing to observe. You are taking a product of these numbers, so that product is strictly greater than the individual number, and additionally you are adding 1 to that, so N is definitely more than every individual Pj in that set, right? In fact, what this tells you is that N cannot be in P, because N is strictly more than every element in P. But what is P, right? Remember, here we defined P is a set of all primes, right? And then we just said that N is not in P, which means that N is not prime. Because if N were a prime, it has to show up in this P set, but then we just said that it is strictly more than every element that appears in P. So N is not a prime, and because N is also greater than 1, right? So it has to be composite then. If N is not a prime, then N is composite. That's what it has to be. Okay, so now we are under this assumption that N is composite. And this assumption is basically, we have reached there by a sequence of logical arguments starting with this assumption. Okay, let's just to have a recap. We started with an assumption that the original claim is false, then we had a sequence of logical arguments, we defined this N, and then we did a logical reasoning, and finally we have reached this conclusion that N is composite. N has to be composite if this assumption is true. Great. So now if N is composite, I will write a claim. Given that N is composite, N must have a prime factor. Okay, so N must have a factor which is prime in nature. Okay, so I'll leave it as an exercise, but let me restate what this claim means. So obviously N is divided by, N has two factors, definitely, 1 and N itself, but because N is composite, it has more factors, and one of those factors has to be a prime one. That is what this claim means. So the proof of this is an exercise. Okay, but suppose this claim is true, so let's assume for now the claim is true. For now, let's assume that the claim is true, and let's complete the proof. So because N must have a prime factor, let's say D is a prime factor of N. Okay, which means D has to appear in this P set. Again, why? Because that's all, right? That's all we have. P is the set of all primes. So if D is a prime number, it has to appear here, correct? So D must appear in this P set. Okay, so this is first part, right? Now let's look at every Pj in the P set. Okay, we look at every Pj in the P set. What does N divided by Pj give you as a reminder? When you divide N by Pj, you get a remainder of 1. Why? Because the way N is defined, right? So Pj is somewhere here, right? No matter which one you choose as that Pj, when you divide N by that Pj, this remainder 1 has to appear. Okay, which in fact tells you that no Pj in P divides N, or in other words, N doesn't have any of these Pj's as a factor, and this is part 2. But then you get contradicting statements here, right? Contradiction is typically shown with this symbol, so this means we have got a contradiction. And what is that contradiction exactly? Here we are saying that N has a prime factor D which must appear in this P set. That means one of the things in P set must be a factor of N, but here we just said that none of the things in P set divides N. Okay, it cannot be a factor of N. So these two statements are contradicting with each other, And we are able to reach this contradiction because here we came with this conclusion that n is false composite, and this conclusion is valid as long as this initial assumption is valid. Okay, that means given that we are reaching a contradiction, our initial assumption has to be false because we have reached that contradiction with a sequence of logical arguments, which means that this original assumption is false. In other words, the original claim that we started with, the statement of the claim, has to be true. Okay, and that's the overall idea of proof by contradiction. We start with the assumption that the claim is false, and then we do a sequence of logical arguments to reach a set of statements which are contradicting with each other. And that contradiction is inevitable given the assumption that we started with. And since contradictions are kind of absurd things, the assumption that we started with, something is wrong with that, right? The assumption has to be wrong, and therefore the original claim is true. That's how the general proof by contradiction works.